Hi everyone, okay, we meet again in a part 3 of group 14. Okay, now today I will explain to you about the relative stability of positive 2 and positive 4 oxidation states in oxides, chlorides and aqueous cation. Okay, before I go further to the relative stability of positive 2 and positive 4 oxidation state, let me introduce about group 14 elements. Alright. Okay, for group 14 elements, it is special than another element because this group 14 can exhibit two stable oxidation state which are positive 2 and positive 4. Okay, so for positive 2 is a monoxides. Okay, and for positive 4 is dioxides. Okay, so how to show example I give to you. Okay, so for monoxide, okay, CO, okay, this is the monoxide of carbon monoxide. Okay, for C, okay, we plus 2, okay, oxidation state of O, which is negative 2 equal to 0 because molecule. Okay, and then carbon equal to positive 2. Okay, so monoxide is the positive 2 oxidation state of carbon. Okay, so for dioxides, okay, we have C plus 2, okay, negative 2 equal to 0. Right, so carbon dioxide is a positive 4 oxidation state. Okay, alright. So, okay, why for group 14 it have two oxidation state? Okay, let we see to the electronic configuration of carbon. Okay, for carbon seat, okay, I just use valence electron configuration. Okay, for carbon, okay, we have 2s2 and 2p2. Okay, so 2s, okay, and 2p. Okay, right. So for okay, in monoxide, which is positive 2 states, group 14 it's only involved only the outermost p electron. So only electron in a p orbital only involved in form bond. Okay, while for dioxide, okay, configuration 2s2 and 2p2. Okay, 2s, 2p, okay, and then we excited it. Okay, it form, okay, one, okay, this one originally, then we excited lah. So, okay, ini to p, then it form sp3, sp3 is 1, 2, 3, 4. Okay, for dioxide, the element make use all the outermost s and p electrons to form bonds, right? That's why for group 14 element it can form positive 2 and positive 4. Okay, so now we back to our chem book notes, right? Okay, this is the summary of relative stability of positive 2 and positive 3 oxidation state. Okay, for the first thing, when we talk about the relative stability, I want all of you put this graph in your mind. Okay, you must memorize this pattern of graph, which is we have relative stability against group 14 elements. Alright, so now what we can see from the graph, okay, the relative stability of positive 4 oxidation state element decreases down the group. Okay, which is for positive 4 oxidation state, it's going down the group, it's become decreases. Okay, while for positive, the relative stability of positive 2 oxidation states, okay, of the element is increases. Okay, increases down the group. Alright. Okay, and then you must know to plot lah. Okay, for the first thing is you tengok sini. Okay, here is the refer to lead. Okay, and then here is refer to tin. Right. Okay, and then followed by, okay, then germanium. We have germanium, we have silicon, and we have carbon. Alright, so this is the graph pattern of relative stability of positive 4 and positive 2 oxidation state of group 14 element. Okay, from this graph, what we can conclude that for carbon, silicon, germanium and tin, okay, the positive 4 oxidation state is more stable than its positive 2. Right? Okay, what for lead? Lead have greater, which is more stable of positive 2 oxidation state compared to its positive 4 oxidation states. Okay, in explaining the relative stability of positive 2 and positive 4, okay, actually I already list down the three reasons why this graph happen lah. The first one, we will prove by show its oxides form. Okay, second, we compare its standard electrode potential, and the third one, we explain using inert pair effects in electronic configuration of lead. Okay, for the first one, it says that the positive 4 oxidation state of carbon, silicon, germanium and tin is more stable than the positive 2 oxidation state. Alright, and then positive 2 compounds are good reducing agent, okay, where they can be oxidized to positive 4 oxidation state. Alright, for example, we see that for carbon monoxide, silicon monoxide, germanium monoxide and tin monoxide is unstable, which is, okay, when it react with oxygen, okay, when it heated, okay, with oxygen, what happen is, okay, it will oxidize to CO2. Alright, okay, and then balance the equation lah. Okay, so same goes to silicon. When it heated, okay, with heat, okay, when it heated with heat, it will get SiO2. Right? Okay, for germanium monoxide, when it be heated, so it will form germanium dioxide. Okay, 2 mole and 2 mole here. Okay, and finally is tin monoxide. Okay, when it be heated, so it will form tin dioxide. Alright, this shows that for tin monoxide, which is positive 2 oxidation state, is unstable because it's easier to form positive 4 oxidation state, which is positive 4 is more stable. So we can see that here is a, okay, positive 2 is being oxidized to positive 4. So this carbon monoxide, silicon monoxide, germanium monoxide and tin monoxide is a good reducing agent, okay, because it can oxidize from positive 2 to positive 4. Okay, we take a look the oxidation state of lead. Why lead is a positive 2 is more stable. Okay, refer to the oxidation state. Okay, so we can see from the reaction. So lead, okay, lead dioxide, okay, is will form, okay, lead monoxide, okay, plus oxygen. Alright, so this one 2, so this one is positive 4 oxidation state and lead monoxide is positive 2 oxidation state. Okay, so That one is positive form reduced to positive to oxidation state. So we can say that lead dioxide, lead 4, which is positive oxidation state compound, are good oxidizing agent. Oxidizing agent, because it tends to reduce the positive 4 to positive 2 oxidation state. Okay, for the second explanation is in compare the relative stability of group 14 is by using the standard electrode potential as we learn in chapter 2. Alright, so the relative stability of positive 2 and positive 4 oxidation state can also be deduced from standard electrode potential, which is the standard electrode potential of M4 plus, to form M2 plus for germanium, tin and lead are shown below. Alright, so for lead 4 plus, for lead 2 plus, the reading of inert cell is positive 1.69 volt. Right, while tin 4 plus to tin 2 plus, the reading is positive 0.15 volt. Alright, and then for germanium 4 plus to germanium 2 plus, so that one is a standard reduction potential class. So the reading is negative 1.60 volt. Right, so this is the standard reduction potential SRP that I already gave you as a reference. Right, so for more positive, the E naught value, that is more positive. More positive, so it will be, it tend to occur the reduction process. So it's easier to reduce lah. So that's why from here we can say that lead 4 plus is easier to reduce to form lead 2 plus, because it is higher tendency to reduce itself. Right, at the same time, that the reagent can be SOA, which is stronger oxidizing agent. So that means lead 4 plus is tend to act as a stronger oxidizing agent. Right, so from our notes, so an increasing E naught value shows that the tendency of the positive 4 to reduce to positive 2. So this indicate a decreasing stability of positive 4 oxidation state down the group. The third part in explaining the relative stability of lead. Why lead is more stable of its positive 2. So we can use inert pair effects. Right, from this inert pair effect, the first thing is we must write down the electronic configuration of lead. Before I write the electronic configuration, how it will be like this. For the first thing is we must apply the Aufbau Principle. So make sure that, I hope all of you already know the definition of Aufbau Principle. So 1s, 2s, 3s, 4s, 5s, 6s, and so on. We have 2p, 3p, 4p, 5p, 6p, and then we have 3d, 4d, 5d, and 6d, and then followed by 4f, 5f, and so on. So in order to apply the Aufbau Principle, write down this arrow. Right, and then arrange the electronic configuration. Followed by 1s, 2s, 3s, sorry, 2p. Okay, we have 2p, we have 3s, followed by 3p, okay, followed by 4s, followed by 3d, okay, 4p, okay, 4p, and then 5s, okay, followed by 4d, okay, 5p, 6s, okay, we must follow the arrow going down, okay, and then 4f, 5d, and 6p. Okay, so now let's write down the electronic configuration of lead. Lead 82. So I want to use shortened electronic configuration. I use krypton. Okay, so 36, and then followed by 4d. Okay, 4d10, 5s2. Okay, and then 5p6. Okay, 5p6, okay, 6s2, okay, and then 4f14, and then 5d, 10, and 6p2. Alright. Okay, so we take a look for the last 4 orbital. Okay, so we have 6s here. Okay, 6s. Okay, 1, 2. Okay, and then 4f. 1, 2, 3, 4, 5, 6, 7. Okay. Okay, 4f have a 7 orbital, which is it's fully filled by 14. Okay, electron. Okay, and then we have 5d. Okay, 1, 2, 3, 4, 5. Okay, 5d consists of 5 orbital which are occupied by 10 electron. Alright, finally the outer one is the 6p. 1, 2, 3. Okay, so 6p is only occupied by 2 electron. So now, can you see that, okay, how this outer electron is want to excited to its higher energy level? Okay, suppose 6s must excited to 6p in order to form bonding, but this, okay, so this is the poor shielding, okay, which is for f and 5d. So the poor shielding, okay, in that. Right, so because of the energy difference between the 6s and 6p, sub energy level is high. Okay, so 6s and 6p very high energy. So that's why the two 6s electrons will remain as an inert pair that will not be involved in chemical bonding. Okay, so it cannot be excited to 6p because of the higher energy level. Okay, so therefore lead is more stable for positive to oxidation number. Okay, so all the chemical bonding, okay, only involve the 6p orbital. So that's why it's only positive to oxidation state is the most stable for lead. Okay, in answering the question of inert pair effect, so you can give the example, some example of chemical equation involve the lead lah. So example you can give is lead tetrachloride, okay, which is liquid tetrachloride. So it easier to decompose into lead dichloride. Okay, it will decompose lightly, okay, to form chlorine gas. Okay, and the second equation you can give is lead O2, which is it will decompose into lead monoxide plus oxygen gas. So balance the equation. Okay, so both thermal stability of lead, which is positive 4 being reduced to positive 2 oxidation state. Alright, so this shows that lead is more stable in its positive to oxidation state. Okay, so finally, what can we define about the inert? Okay, the inert pair effects. Okay, inert pair effects in lab is, alright, the reluctance of the electrons in the outermost, okay, 6s orbital to take part in chemical reaction. Okay, which is only use the 6p electron in any chemical reaction to be occurred. Alright. Okay, for the last one, for this relative, I want to explain the differences between the electronic configuration. Okay, now in my chem book, if you can see, this electron configuration is krypton 4d10, 5s2, 5p6, 5f14, 5d10, 6s2 and 6p2 is different from the electronic configuration, okay, that I explained earlier. Okay, why? Okay, so the below electronic configuration is only used in order to explain about inner pair effects, okay, about the graph pattern. Okay, why for this electronic configuration is you must written like this when you want to explain about the three principles, okay, which are Pauli exclusions, Hans rules, and Aufbau Principle. So you must follow these three rules in order to write the correct electronic configuration. Okay, so thank you. We see again.